the emissions. We will have the carbon dioxide that we form by burning the gas to create the energy in the process. We, of course, will make liquid the nitrogen that we need to reject. And I'm sure there would be some amount of venting required to maintain material balance. But the emissions are very low from the process. Maybe I just did not understand the question.
No, I was thinking about when you utilize this aviation fuel in the...
I'm sorry, you'll have to speak louder.
When you utilize your aviation fuel that you produce with your process, how does it compare in terms of combustion emissions with conventional aviation fuel?
It would be about the same as any other aviation fuel, I assume, except there's no sulfur in it. What we've done so far is the man I showed you standing in the picture took a jar of this fuel home and mowed his lawn with it. And the lawnmower ran beautifully and produced very little smoke. In fact, you couldn't see any smoke coming out. Getting more adventuresome, he then took some and mixed it with regular gasoline and put it in his car and drove it and had no ill effects there. So you're still going to get carbon dioxide and water out and some unreacted hydrocarbons.
I was thinking about NOx formation.
Yeah.
Short question. Once you arrive at ethylene, why shouldn't you stop there? And it seems to be a very competitive route to produce ethylene.
The whole point is this process would produce the ethylene. There are thousands or millions of things you can do with the ethylene, of course. We assume that if you go the ethylene route, that you have a chemical plant sitting nearby that you would require the ethylene and or the hydrogen.
Do you see it as a realistic option to stop at ethylene?
Yeah, we just say that this process will produce the ethylene for you, and we believe it's very competitive compared to regular ethylene crackers, especially when you consider the low rate of coke formation here compared to the ethylene crackers. But yeah, I could draw anything on the other side of the ethylene.
Would you have any safety concerns with this chemistry?
Safety concerns? Well, of course, we're operating at very high temperatures in the cracker burner. And when we were operating in pilot plant mode, where we would start it up, run it for a day, and then shut it down and analyze, and start it for a day and shut it down and analyze, the thermal shocks to the cracker would cause leaks. And as soon as a small pinhole leak occurred, it would obviously melt down the reactor because it would just come right out. When we operate in demonstration mode, of course, the thermal shocks are not there, and so the reactor seems to work very well. However, we also have the experience of the acetylene industry before the war, where these reactors would perform well for long periods of time. The acetylene, of course, is always a safety concern. If you operate with the gas phase hydrogenation, then it's necessary to keep the acetylene concentration below 2% mole percent to be sure that it will not auto-ignite. Operating with the liquid phase hydrogenation, it's possible to go up at least to 20%, and probably we could stretch that some. Other than that, it's a hydrocarbon process, and certainly there are always safety concerns. We did do a thorough HAZOP before we ever started the pilot plant, and then another one before we started the demonstration.
I'm afraid we need to stay on time, so I propose we thank Dr. Hall for this very interesting presentation. So the next presentation is, I assume it's given by Dr. Sinev. Okay. So Dr. Sinev from the Sinev Institute of Chemical Physics in Moscow. And as you can read the title, of this conference.
morning, ladies and gentlemen. First of all, I would like to thank the organizers for allowing me to speak about this process, which is a kind of marginal thing nowadays. It was the topic of the day about 15 years ago, but nowadays it goes very, very to the margin of the GTL and natural gas to chemicals story. But what I will try to, during my presentation, I will try to convince you that there is still a room for this process. I would like to start from this map. You see, this is Russia. It's quite a part of the world. And in this color, where is it? Oh, it's here. You see this color on the map. These huge territories are gas and oil provinces in Russia. And this is the scale. This is 1,000 kilometers. Here you have a number. In order to build a pipeline of 1,000 kilometers, you have to pay about $1 billion US. It's quite a number. In order to collect gas from such huge territories, you have to build a huge pipelines because you need a network. So that means that there is one more problem. If we want to transport gas in pipelines, now we are paying about 10% of the whole amount of natural gas taken from the ground to pump the rest. So this is really a very, very serious problem. There is another problem. If we look at the distribution of natural gas in different gas fields, we will see that only some part of gas fields contain enough gas to build huge GTL plants of the type we had heard about during last 2 days. But in other gas fields, the amount of gas is not as huge. And in order to build some plants or to create some technologies which are able to convert this natural gas to any product which we would like to have, we have to think about different technologies. But as far as Russia is concerned, we just hardly need new technologies which can work efficiently at a lower scale of operation. And the aim of this presentation is to demonstrate the feasibility of alternative GTL technology via oxidative coupling of methane. This is the outline of my talk. I will not stop in detail on the outline, and I will go to the content of the presentation. Of course, natural gas has high caloric value, but it has a low density. That means that we need some ways to make the transportation of gas, of the high caloric capacity of the natural gas to the final customer to use it somewhere on large distance from the place where we take the natural gas from the ground. And of course, syngas route is one of the possibilities. Another one is the OCM route, which I will speak about in more detail later. And there is a third route, direct conversion of methane to methanol, and I will not speak in detail about it because later this morning Professor Arituno from our institute will speak about it in more detail. So I will stop more on on the comparison of the two routes, namely syngas route and OCM route. Let me first speak a little bit about the chemistry of the process. Not just about chemistry, but let's now speak a little about thermodynamics. If we look at the energetics of the transformation, on the free energy of transformation of methane into the final products, in this case synthetic liquid fuels, we will see that if we use reforming with no oxygen, we will have to pass through a very high barrier. The first stage for the production of intermediate product is very strong uphill, has very strong uphill nature. But if we go to oxidative routes, for instance, if we go to oxidative reforming, we go downhill. In the case of oxidative coupling, we have ethylene as an intermediate, and we also go downhill. And the final process, the second stage, is also a downhill process. So we can go smoothly from methane to the final product if we go oxidative. So these are the messages from this picture. And but also what is important in both these cases, if we want to run our processes autothermally, we still have to burn a certain part of initial natural gas because neither in the case of oxidative coupling nor in the case of oxidative reforming, our catalyst can work at temperatures which can be calculated as adiabatic temperatures in these two cases. So we still need a burn of part of the initial natural gas in order to run these processes autothermally. That means we will never ever be able to achieve 100% selectivity on a carbon basis in the case of OCM or in the case of oxidative reforming in terms of carbon and hydrogen efficiency. A little bit about the history. Probably many people in this audience remember this oxidative coupling boom, which appeared in early 80s after pioneering works of people. Some of the names are now on the screen, but after about 10 or 15 years of the development of the area, it went to the state of frustration and fading. And there were certain reasons for that. First of all, I believe that this was due to some stabilization of world oil market, relatively low per pass yield in the oxidative coupling. We cannot achieve more than 15% of ethylene per pass because of very strong kinetic limitations. And also because of the free radical nature of the process. Although it's a catalytic process, it has a free radical nature. And it's a very serious problem of scaling up and stable operation of the process because of its free radical nature. But at the same time, namely its free radical nature allows it to take place. Because we have, if we speak about the microkinetics of the process, we have what I call OCM window in the range of temperatures between, say, 600 and 850. When on the left-hand side we have a strong decrease in the value of the equilibrium constant of methyl reaction with oxygen in the gas. And on the other hand, in this temperature interval, the reactions of direct burning of methyl radicals are not important. So in this temperature range, this radical chemistry in the gas phase allows OCM process to exist. Now I go a little bit to more technological aspects of the problem. As I told you, there was a boom in oxidative coupling, and in many places, in some places in the world, in the United States, in Europe, in Japan, some pilot plants were built, as far as I know. Of course, this is not very open information, but it's known. Now we are trying to give a new life, I would say, to this technology. And on this chart you have an imagination of how does tentative ethylene production scheme look like. This upper part in white is the production of crude ethylene, but this bottom part is the part which allows us to separate the ethylene from the reaction mixture and to lead it to the conditions at which we can use it as a source for polymerization. Some estimates demonstrated that if we talk about the product of polymerization conditions, we have to pay about 80% of the primary cost for the bottom part of this picture. But if we go to synthetic liquid fuels, we just can forget about that part, and we can produce in the way similar to the one we saw in the previous presentation, to synthetic fuel, which is very similar to the one we heard about, and just recycle the rest of light hydrocarbons to the feed. And in this case, we can convert up to 70% or at least 60% of natural gas, which is coming into final liquid products. This is a typical composition of reaction mixture which we have in case of one reactor or two reactors put in this series. We can run, of course, in one reactor with this ratio, but there are two issues. One, safety. Of course, we don't want to have explosive mixtures in the reactor. But another one, which I mentioned before, we want to run the reactor orthothermally. So if we have a lot of oxygen going into the first reactor, we have overheating, and we can, the process becomes not sustainable, and it can run away. So we have to reduce the amount of oxygen supplied to the first reactor. But what we don't need to do to separate the mixture after the first reactor. So we can run them in a series with no separation of the reaction mixture. We can have up to 8 or even more percent ethylene on the outlet of the reactor, and we have a certain amount of C2 and higher hydrocarbons which can also be utilized. Just a few words about economics. There are several ways to transform crude ethylene to liquid products: hydration to produce ethanol, oxosynthesis to produce some chemicals which have more carbon atoms in the molecule than ethylene does, and also we can have oligomerization to produce synthetic liquid hydrocarbons. And the next speculations, economical speculations, I will deal with this oligomerization. Here, this is a typical trend of cost of the cost of the price we have to pay for capital investments if we want to build huge GTL plants. And it is very well known, and we heard about that yesterday, that the bigger the size, the less we have to pay for the unit production. But as I told, traditional GTL technologies require very big amount of natural gas concentrated in one place, but we want to build something which is much smaller. And our preliminary economical evaluations demonstrate that if we want to build the plant for production of ethylene for polymerization, we have to pay, of course, more than for the regular traditional GTL. But if we transform ethylene without preliminary separation and purification into liquid hydrocarbons, the efficiency, the economical efficiency could be at least slightly higher. And this means that OCM route can be highly economically competitive. And these are the graphs which show you what can be a product prime cost. Again, we see that if we want to produce pure ethylene, it goes higher than traditional GTL and alternative GTL via OCM route. But still, if we have even natural gas price relatively high, the production of pure ethylene via oxidative coupling can be economical. And of course, in some places in the world, especially in Russia, we have the price of natural gas which is almost negative. So that means that we just have to pay some money to transform to flare natural gas, so that, and we have certain very serious, of course, environmental problems, and that means that the price of natural gas in some locations is just negative. So that means that even if the carbon efficiency in terms of single pass yield and overall yield of the final product is not 100%, still this alternative way of production of liquid products from natural gas can be very feasible, especially in certain locations. And now I go to conclusions. The material which I presented here said that, of course, that this is known from the presentations we had yesterday and probably will have also today, that traditional GTL technologies represent the current state of the art in natural gas processing. But they require very high initial capital investments which are not accessible in many cases. The number of cases when these high capital initial investments are not accessible is much higher than the number of cases where they are accessible. And the alternative GTL technologies require lower initial capital investments and can be efficient and economically feasible at smaller scale of production. And these technologies presently are at the stage of scaling up testing, and now we are trying to achieve the yields which are available in laboratory and a little bit higher scale of operation, because the intrinsic activity, intrinsic productivity of catalysts which we have is sufficiently high, but the scaling up, as I said, is a big problem in this case. And my final remark, I thank all of you for your kind attention. Thank you.
Thank you, Dr. Sinev. I believe we have time for one or two questions.
What is the type of catalyst that you would be thinking of?
there is a big number of catalysts. It depends on the final, I would say, on the second stage, because this process can be optimized in different ways. In some cases, if we speak, for instance, about polymerization, we have to have as low concentration of carbon monoxide in the reaction mixture as possible, because this is the most serious problem in terms of separation. If we talk about, say, alternative GTL processes or some similar processes, in some cases, if we talk, for instance, about oxosynthesis, we have to have more CO and hydrogen simultaneously with ethylene in the reaction mixture. And this is a subject, the catalyst which we use can solve some downstream problems in the reactor, in the OCM reactor. So we have plenty of catalysts. Depending on the downstream process which we choose, we can use different catalysts. For instance, a rare oxide catalyst and some other systems which are also very efficient.
Yes, final question?
Since you haven't yet chosen the catalyst for the second step of taking the dirty olefins to fuels, what were you assuming in the economic model was the carbon utilization from the total carbon in your mixed olefins to the fuels?
If I understood you correctly, for economical evaluations, yes, we assume that we use the total carbon efficiency is say about 65%. So even at that level, this is not an optimistic, of course, but it's a kind of realistic because of first of all because of the scaling up problems on the OCM stage.
Okay, thank you very much, Dr. Sinev.